All right, so I'm going to try to keep this as simple as possible. Let me get a full screen so I can see. All right, so let's get started. In this video, I'm going to talk about how important it is to understand the differentials of exponential functions and logarithmic functions. And if you understand the differentials, then you can graph these types of functions in 10 seconds or less. The mechanics becomes very easy, and you can see where each of the numbers comes from. You have to get a feeling for a couple of things. Most importantly, you need to understand why b to the 0 is 1 and why log base b of 1 is 0. We've had those discussions now in our first 7 weeks of classes, and hopefully you're beginning to get a good feel for that. All right, so that's some preparatory work. I'm assuming you know that now. I'm basing this video on the fact that you've got some experience with that. And if you don't, well, we've started the conversation here. All right, so let's look at an exponential growth model. All right, I'm doing that correctly. All right, and the differentials are the difference between the constant, right? A horizontal line is a constant, and the height of each differential. And the base of exponential models comes from the second differential, the one on the right, divided by the one on the left. That's what we're going to see in a moment here. And when I do the inverse, we've been studying the inverse of exponential models. They're logs, right? Log base 5 of 25 is 2. 5 squared is 25. Same information, but said one in one direction and then the inverse. So I'm going to switch the x's and the y's. That's how we get inverse functions. So I'm going to switch it here, and then you can see the logarithm has differentials. In the exponential models, the differentials are vertical. In the log, they're horizontal. We're going to look at a couple of functions and spot where do I look for those differentials? Because if you can draw the differentials, you basically can do these graphs in, I don't know, fastest I think I've seen a student do it is like 5 seconds. All right, so let's see if we can get there. All right, so I've got the easiest exponential to understand is doubling. All right, I think, you know, we get a feeling for that, something doubling. And I tried to look at the differential on the right, and I tried to draw it to be about twice the size of the one on the left. And if we put the numbers in that go with this, we want to make 2 to the 0, and we want to make 2 to the 1, because it's real easy to work with those numbers. So I hope you can see that if I put 1900 in, I get 2 to the 0, which is 1. 1 times 8 is 8, and 3 plus 8 is 11. And then if I go forward 124 years to 2024, and I drop that in for the time, then I get 124 divided by 124, which is doubling this 8, which makes it 16. All right, and 16 plus 3 is 19. Okay, and if I have a horizontal and I switch my x's and my y's, then a equals 3. I'm basically saying time to amounts. Exponential models, you know, you might think of a petri dish bacteria with a certain amount of initial condition, and if that differential is doubling, all right, so the next one would be 16, so on and so forth. All right, I think you're looking at it here. All right, so I keep this simple, coach. So we're going from time to amount, and the inverse of that is amount to time. And so our x-axis on the left is a time axis, and our x-axis on the right is an amount axis, right? Where I give you the amount of bacteria in a petri dish, and you tell me at what moment you have that amount. All right, so trying to keep it simple here. So if we start with an initial amount of 3, I'm putting things on top of 3, all right, and we get this curve that we saw a minute ago, something like that. And I hope you can see that if we look in the past, 124 years in the past, that would be 4. Another 124 years in the past, that would be 2. And I think you can see how that is, you know, that part of the calculation is approaching 0 on the left, which means we're really approaching the number 3 on the left. And on the right, bigger and bigger and bigger as we go along, going to infinity. And so what is the inverse of a vertical differential? A horizontal one. So over here, the inverse of A equals 3 amount, I'm just going to write in terms of X's and Y's, I think. So I'm going to change this amount based on X. Otherwise, I'm going to have to think about what I'm doing, and I don't want to have to think. I just want to show you mechanically that we can do these pretty simply. And so over here, I am going to, again, work with X, and we'll just call this f of X now. So let's call that, well, it's going to become the inverse. And so instead of A of X, let's call it f of X. Let's stay more traditional. And I think that might actually allow this video to be done more quickly by me. I'm getting up there in age, and sometimes I lose my train of thought, and then I got to scrap the video. So let's keep going. So over here, we have y equals 3, or f of X. Let's say, y equals this. Get that out of the way. So we got our y equals 3 asymptote. So over here, the inverse of y equals 3 is x equals 3. So I'm going to need x values that are bigger than 3. My first differential is going to become 8. My second differential is going to be 16. And we'll see why in a little while, which means that that one's 4, and then that one's 2, then that one's 1. I'm really getting that trajectory. All right. And now let's actually get the inverse of this function. So let me bring this function over here. 8 times 2, x minus 1900 over 124 plus 3. And you can get exponential inverses by pretending you have some answer over here to an equation. And really, the function is based on solving this equation, the operations that you would use in solving this equation. So let's do them quickly so we can get the calculation in front of us, and we can see how we can visualize these numbers. So I would subtract 3. I would divide by 8. The inverse of log of exponentiating base 2 is log base 2. We've been working on that. Let's move this equal sign over a little bit. Dividing by 124 means we're going to multiply by 124, and then we're going to add 1900. Now I got to put a parentheses around the argument. I'll make that a better 2. All right, and now we can see that 3 plus 8 is 11. 3 plus 16 is 19. And if I put 11 in, I'm going to get 1900. We'll show you why in a minute. And if I put in 19, I'm going to get 2024. All right, and now I'm going from amount of population in the Petri dish to the year. Well, that doesn't, we don't look at years worth of growth for Petri dishes, but hopefully you get the gist. All right, so let's actually see where the number 3 might come from. Geez, I wonder. All right, let's get everything else out of the way here. Let's see. Get this out of the way. Let's get that out of the way. Let's really highlight this graph. Let's take those away for a minute. I wonder where I can get 3 from. Oh boy, I think it's telling me what the asymptote is in the argument. I think I can find it. I'm trying to make a 0. So I'm trying to let x minus 3 over 8 equals 0. Sure looks like x equals 3 is important. All right, and now I've got 11, and 3 to 11 is a change of 8. I wonder where I can see that change in this equation. Change of 8. Pause the video. See if you can see where the change of 8. Oh, yeah, it sure looks like the division in the argument is getting me that. Looks like I got a nice cowlick. That's good. Have some fun here. All right, so I guess if you spot that, you can do that. And 8 plus 3, yeah, that's not hard to figure out what number is friendly. So I guess we're trying to find out when x minus 3 over 8 equals 1, because I think folks know at this stage, log base 2 of 1 equals 0. And I think multiplication by 0 is very friendly. In fact, if you multiply 124 by 0, I think you get 1900. So let's put 11 in, see how it works. 11 minus 3, 8 divided by 8. Oh yeah, gives me 1. Log base 2 of 1 is 0 because 2 to the 0 is 1. We've been studying that. So hopefully you're making that connection. And then if we set, I guess the next one's 16, we got to, again, come up here and say, where can I see the number 16? Geez, 8 times 2. Could it really be that simple? Yes, it can. And 16 and 3 is 19. So let's put a 19 in this time. 19 minus 3 is 16. 16 divided by 8 is 2. And I think we've been practicing logs enough that everybody in the classroom can tell me what exponent you put on top of 2 to get a 2. It's 1. And what's the second easiest multiplication in the world besides multiplying by 0? I think multiplying by 1. I don't think I need a calculator. 2.9387. 2.9387 times 1 is 2.9387. I don't think I need a calculator. All right, so, and then with more work, the next one would be 32, right? And I hope you see the trajectory. Then 64, and moving backwards, 4, 2, 1, we start to get a feel for the calculation. So I'll just put another equation up here. All right, and we'll see if you can graph it. I'll stick with exponential growth. And you pause the video, and I'll just do it. And then we'll look at e to the x and ln of x, and some numbers that are extremely important for you to understand. And then we started the conversation. So what if I said y equals, I don't know, 50 log, let's make that 53. Easier to see in L now. Log base, I don't know, how about we do base 4? And let's do, how about x minus 2 over 7? And then let's add 100. That's a nice, easy addition. Okay, so pause the video and you'll give a go, but this is what I see. I know that 2 is going to be my asymptote. I know that I'm going to move 7 units in this direction, and then 4 times 7, 28 in this direction. I know my trajectory is going to look like that. And then I think I'm looking at the numbers that get me 2 plus 7. Well, that gets me 9. That's going to be right there. And 2 plus 28 is 30. Those are going to be very friendly numbers to work with. So I'll drop a 9 in. I get log base 4 of 1, which is 0. 0 times anything is 0. So that gives me 100. And then I guess I can drop in, oh, I wanted the 100 here, sorry. That was the 9. Then I want to drop in a 28. So let's drop in a 28. 28 minus 2 is 7. 28 minus 2 is 30. So I'm dropping a 30 in here. I'm rushing too fast. 30 minus 2 is 28. 28 divided by 7 is 4. And that gives me log base 4 of 4, which is a fancy way of saying the number 1. And 1 times 53 is 53, and 53 plus 100 is 153, and I'm taking a lot more time with that than I really need to, because I'm trying to get you to see where the numbers work. So the number 100, oh boy, I wonder where I could find that on the first differential. Oh, the number 153, I wonder where I could see 153. All right, so we get a quick graph going, and that's good. That's a good thing, because then we can have conversations for the rest of the semester about how's this really working, where's it coming from, how do we apply it, but we got to be able to understand how the numbers work and what the trajectories are first. All right, so last thing I'll do is e to the x, and I should have already had this written on another board, but there are some numbers that you really got to get familiar with, and they are e to the negative 1.1 is approximately a third. E to the negative 0.7 is approximately a half. E to the 0 we know is 1. E to the 0.7 is 2, approximately. E to the 1.1 is approximately 3. And you need to know that E is approximately 2.71. Absolutely essential for the work we're going to do in the second half of the semester, that you understand these numbers, because we're going to develop the rules of logarithms from our work with them. That's our ultimate goal, is to actually understand where the rules of logarithms come from, to be able to see them. And the sooner you memorize those, the quicker that can happen. All right, so I've got y equals e to the x. I have enough there right now to graph y equals 0, right? So this is an a, b to the x plus c model. And all I'm doing is e to the x. So what's my first differential? So let me put it here. E to the x is being multiplied times 1. I've got x minus 0 over 1 plus 0. So y equals 0 is my asymptote. If I put in a 1, and if I make this 0 by plugging in a 0, e to the 0 is 1, times 1 is 1, plus 0 is 1. So it goes through 0, 1. And if I put a 1 in here, I get e to the 1 is between these two numbers, right? I get 2.71. So I get a first asymptote of 1, and then 2.7. Okay, and I've got my exponential growth model. And we can write all functions in terms of e to the x because the banking system and a whole lot of stuff in physics deals with writing exponential models in terms of e. And so what's the inverse of e to the x? Y equals ln of x. All right, and that tells you the exponent you put on top of e to get any number. Okay, so let's keep this simple. Let me just graph ln of x with the differentials. All right, so ln of x, which is basically the same as log base 2.71 to the x, I'll put this in here, minus 0 over 1. So we can talk about the differentials of this function. So what's the important number in the parentheses? 0. What's my first differential? 1. What's my second differential? 1 times 2.7. What's the graph look like? Looks like that. So this turns out to be your x-axis, where 1 gets you 0. This one is 2.71 gets you really the ln of e, and it's base e, right? So that gets me a differential of 1 times 2.71, and that happens when I put in when I make x equal 1. All right, so this really becomes your x-axis, and the ln of 1, the ln of 1 is 0, that's this one, and the ln of 2.71 gets me a height of 1. Okay, what does 3 get you? 3 would be right about here. That would be 1.1, the inverse of those numbers that I had over here. What would 2 get me? 2 would be right about here. That would be 0.7. Right, and so we're going to learn how to write. I didn't plan on saying this, but I'm going to say it. So what's another way of writing y equals 2x in e notation? It's approximately e to the 0.7 gets us 2. If I put an x there, I'm really mimicking 2 to the x. So it's approximately e to the 0.7x, which means that I can change all kinds of exponential growth models very easily by getting familiar with different values of exponents on top of e that give me simple numbers like 2, 3, 5, 6, things like that. That's where we're headed. All right, I'm starting to ramble. I didn't want to do rambling at all in the video. So that hopefully gets the conversation started. We'll have this conversation in class. You can look at this video, at night to try to remember what we're starting to talk about in class. And the more times you consider this conversation, at some point, I hope the lights go on. All right, enough of that. Ta-ta.